So while we wait, I'll just do a quick introduction for our next speaker, Qi He. Qi is the Senior Director of Engineering at LinkedIn, leading a team of over 150 machine learning scientists, software engineers, and linguistics specialists to standardize LinkedIn data and build the LinkedIn knowledge graph by creating standard entity vocabulary, recognizing entities, and building entity relationships, and using this data to serve the entire LinkedIn ecosystem, including member engagement and monetization products. She has over 15 years of experience managing and executing large complex AI products in knowledge mining and management, recommender systems, information retrieval, and language process with big business impact. She will be giving us a talk on constructing knowledge graph for the world's largest professional network. Please give a warm welcome in chat, and I will hop off.
Yeah, hello everyone. My name is Qi, and once again, sorry for the inconvenience. And I come from the data standardization and knowledge graph team at LinkedIn. So today I will introduce to you our work on constructing a knowledge graph for LinkedIn, the largest professional network in the world. Next, please. And next. Yeah, a quick introduction. So although most components in LinkedIn knowledge graph are the same as a general knowledge graph, right? But there are some unique characteristics and challenges at LinkedIn. So on the left side, our input is the member profile of our ex-CEO, and we also process the job posting, company page, news article, resume, and so on. So the input, you can see, right? The input has a lot of text, either unstructured in some part or semi-structured in other part. So we need to transfer those texts into well-defined, well-structured data, like what is displayed on the right side. So the output on the right side is the knowledge graph centered at this member. So constructing the knowledge graph for social network members is a very challenging task, mainly for two reasons. The first, we are processing for every member. LinkedIn has more than 800 million members. So the input data for each member in the social network is noisy, implicit, and in multilingual. So noisy means the user can type anything, even a typo for her title and implicit means the user may not explicitly say, oh, I know this, I know that in her profile, but implicitly describe a related thing. So the multilingual means the user may type non-English in her profile. So the input data is noisy, implicit, and in multilingual. So the second challenge is the knowledge graph for social network is not static. It will grow when the social network grows. On the contrary, the social network will also grow when the knowledge graph grows. So their interaction are affected by multiple organic feedback loops. So these two challenges fundamentally actually differentiate social networks knowledge graph from Google or Amazon knowledge graph. The Google or Amazon knowledge graph, they are more static as they are mainly about the real world factors. So the social networks knowledge graph is much more dynamic over time. Okay, thank you. Next, please. So, but the challenge also actually give us a lot of opportunities, right? So and we believe the best strategy to tackle this technical challenge is developing some deep and holistic method. So because of the input data is noisy and implicit, so we need to develop very deep NLP graph learning models to deeply understand the input data. So because of the social network and the knowledge graph grow together over time, so that's why we need to model their interactions jointly and then refine one using the other. So that's the opportunities. Next, please. So in today's talk, I will give you an overview about LinkedIn knowledge graph first, and then we dive into three technical challenges. The first one is how can we use the transfer learning to address the internationalization problem. And the second is to leverage the social network to enhance the knowledge graph construction. And the last one is how to leverage the graph structure for knowledge graph construction. We also have a tutorial given in the World Wide Web conference. You can see our video record in YouTube and some recent published papers. Next, please. Okay, first, an overview of the linking knowledge graph and the application. Next, please. Yeah, so linking knowledge graph, also named as the economic graph, contains billions of entity nodes like we have more than 800 million members. We have more than 1 billion jobs. We have more than 100 million organizations like companies, schools, and we have a lot of titles, skills, geolocations, degrees, and so on. And between these entities, we can also create billions of entity relationship edges, so that the entire graph is complex and dynamic. Let's just use the member and the skills as one example to introduce the linking knowledge graph in these slides and also in the following slides. So we have more than 800 million members and 50,000 skills. So member entities are self-created by members, and the skill entities are created by linking. Next, please. So over the past more than 10 years, linking created our own skill taxonomy. So where the skill vocabulary is used to represent linking members, jobs, and courses. So here's one example for a specific skill, graphic design. You can see in the taxonomy, we describe the definition. We have the canonical name. We also have the aliases in different languages. And we also describe what the skills type. And also we build a hierarchical structure with other skills. For example, let's say the parent of the graphic design is design, and it has a children called Photoshop. Okay, next, please. Okay, now we have members, we have skills. The next question is how to build the connection, build the relationship between the member and the skill. So let's take a close look at this member's profile. We need to understand the skills this member has, right? So we have multiple highlighted skills using the rectangle to highlight those skills. Those are the skills mentioned in the member profile. But wait, not all skills actually mentioned in this member profile are the skills actually the member has. Because if you take a closer look, you can see those green box skills. They are not the skills of this member. They are actually the skills about the company this member is working for. And we also have some skills not related to this member that much, which is those skills in the bottom inside the red box, right? So those skills has a very low confidence score. So we need to remove all of them. So, and then we can safely say, oh, the left skills, for example, let's say the two skills mentioned in the title of this member are the actual skills this member has. So from this example, you can see the actually the building the relationship between the member and the skill. It's a difficult problem, but there are a lot of noise inside the text. And this is just a teeny part of the whole linking knowledge graph, given we have so many other type of entities and so many other type of entity relationships. So next, please. Next, please. Oh no, sorry. Can you go back to the original one, previous one? Yeah. And after building the linking knowledge graph, right? So we serve the data to empower all the linking products. You can see that we have so many examples here. So yeah, almost every product at linking use our data, and our members are facing the knowledge graph service on a daily basis. For example, when they search for a job or see an ad, when we recommend them a course they should take, or when we create the monthly economic graph report. So this product use our data explicitly. And whenever we have a major update on the data, we also run the A/B test for this data update to measure the product impact, like revenue and user engagement directly. And the other product use our data as features in their machine learning models. Okay, next please. So when the knowledge graph is used more in product, we can receive more user engagement signals from the product. And this signal can enhance knowledge graph construction. A better data then actually deliver more values to the product by driving more user engagement. So such a positive flywheel effect, really boosts the knowledge graph to the next level. Okay, so with this quick overview of the linking knowledge graph, I'm now going to go to the 3 technical challenges I just mentioned in the beginning. The first one is, next please, the first one is the transfer learning for multilingual knowledge graph construction. Next please. So the problem is let's say we already built a knowledge graph for English users. Can we build a graph for the Spanish users? Next, please. The challenge is usually because building a knowledge graph requires a lot of human annotation, human labeling. So when we use the deep learning to build connections between 2 entities, this requires a lot of training data. But the challenge is not every language has so many annotation data as the English. And also annotation in a new language is very time consuming. So the idea is how can we solve this problem? Next, please. Okay, so the idea is the transfer learning. What does this mean? This means that we use the English data to train the English model. And then we transfer the knowledge from the English model to the Spanish model, which means that we can use English data to train a knowledge graph for the Spanish users. Okay, let's see actually how it works in the next page. Okay, assume we have training data in English, and we also developed a machine learning model in English. Can we use the data in the model for other languages? Next, please. And to answer this question, we need to introduce some very basic concepts, so-called encoder and decoder. So encoder and decoder is the machine learning framework, right? Encoder means that we generate machine learning features, and the decoder means that we use the feature to do the classification. And for example, let's say the one type of classification is to predict this member has this skill, right? Now, with this framework, right? So the question is so can we use the English features? Can we use the model actually, the trend using the English data for the Spanish? So if you go to next page, please. Yeah. So the idea is is simple. If we can encode the same kind of features from both language, then we can reuse the same decoder because of the feature is the same, right? If the feature is the same for both English and the Spanish, then the decoder part, the classification part, can be exactly the same. Okay, now all the challenge boils down, how could we generate the exact same kind of features from two different language. Okay, next please. Okay, so one solution is to use the multilingual word embedding. So the word embedding means we use a vector to represent the English word, and we also use a vector to represent a Spanish word. If let's say if the translation of the English word in Spanish has the exact same embedding, then we can use embedding as the features. Because of the embedding feature for both language, they are the same. So that's the ideal. So the multilingual word embedding, the magic is they can actually embed two language into the same space. And if these two words, X is English, Y is the Spanish, if these two words they are the translation of each other, you can see they can be embedded into the same point in this space. Then we can use the embedding as the features. So that's the ideal. This require we have a parallel word dictionary X and Y. X is English, Y is the Spanish. So which means this require we do have the dictionary to map one English to another Spanish word. With this dictionary, we are able to construct these embedding features, which is same to both language. So that's the ideal. Next, please. Okay, if you say hey, if I do not have, let's say if I don't have the dictionary, I don't know how to map them English to Spanish. How can I do? So in the machine learning, there's another idea called the adversary learning. So I'm not going to go to the technical details, but the basic idea is to use this adversary learning, and we are able to actually approximate the translation. So, okay, next, please. Okay, so the conclusion is we can reuse the English models to develop models for other language. And the method is using the multilingual word embedding if we have the parallel word dictionary. If there's no parallel word dictionary, we can use the adversary learning to learn the embedding. So let me actually pause here for a few seconds in case there's any question. If no, we can move to the next one. Okay, so the next technical challenge I want to introduce here is how to leveraging the social network to refine the knowledge graph. Next, please. Okay, let's still use the member skill relationship as the example. So the idea is, okay, instead of actually using the machine learning to predict the relationship between member and the skill, we can directly ask our members to just ask them, hey, are you good at this skill? What's your expertise level at this skill? We can just directly collect this kind of data from the members. LinkedIn has a lot of active users who are willing to provide this data to us. But the challenge is if you ask data from user, some user can game and manipulate our product, right? So they can say, oh, I know everything. Right? They can endorse other people without any constraint. So how can we mitigate the gaming and the manipulation? So the idea is first we design multiple products, and let's use the multiple products to collect the same kind of data and create some redundancy. And we hope actually it's harder to gain multiple products at the same time. So that's the one idea. And the second idea is we force user to choose one option from multiple options, and so they cannot, they have to make a comparison. Then this actually can mitigate the gaming. So here I can give you some examples. So the first example on the left is we just ask a member, hey, how good you think this person at this skill. We give you 3 options, right? Good, standard, and highly skilled. And you are forced to pick one of them, right? And on the right is the second product, right? So on the second product, we ask you to endorse Jenny's top skill, and then we'll give you 4 options: Java, UX design, or other skills. You cannot you cannot actually apply all of them. You have to pick only one from the 4 skills. This actually forces you to do a comparison, then to mitigate the game and the manipulation. If you next, please. Yeah, the third product is we ask you, hey, who is the best person for you to get for you to ask for questions about Java? Who is the person actually that you like to treat her as expert in Java, right? So again, you have to make a selection among these 4 people, not all of them. You have to select only one, right? So you see, with the 3 products, and we have more than 3 products. We in total designed 7 products. So and for each product, we force you to make a selection. So then with this, hopefully we can mitigate the gaming and the manipulation. Okay, next, please. Next, please. Oh yes, here. Now you see we have in total here's 3 examples, but in total we have 7 products, and we use those 7 products to collect the same kind of data and force you to make a selection. Then how can we finally output a single data, right? So here we use another machine learning technology called multitask learning. The idea is we treat the input from 7 products, and we learn a probabilistic model to learn the weight of each product, and then we do a weighted average, and finally actually output a single score, how good this member at this skill. So, and with this kind of multitask learning, we can further mitigate the member gaming in one particular product. All right. Next, please. Okay, so this is just some other examples, because we talk about the member to skill, how to collect member to skill data. Here, we also actually ask a lot of the pre-screen questions when people apply for a job, and to better understand the jobs and to better understand the members. So that's another type of the product, actually, how we collect data from user directly to construct the knowledge graph. You can see there are some external articles to report our product progress in this work. Okay, next, please. Yeah, the third one is the how to use graph modeling for knowledge graph construction. Yeah, next, please. So we use the very advanced technology called GNN, which is the graph neural network. It's a very advanced deep learning model. So the reason we use the GNN, graph neural network, because of the graph neural network actually is very suited to the graph structure. And linking data itself, right, is a graph structure, right? So that's why we believe actually use the GNN model, we can better understand the member, better understand the job, for example. So precisely. So to construct a GNN model, it requires 3 steps. The first step is given a node A, right? A is a member, for example. Given node A, we want to create embedding. We want to create a semantic embedding for this node A. So the idea is let's travel the A's neighborhood, BCD. BCD are the A's neighbors in the linking graph. And this is the first hop neighbors. And from the B also connected to A and C. That's the second hop neighbors. If you keep traveling this graph, you can create a graph centered at the node A. And we call this graph computation graph for the node A. Okay, next please. Yeah, so with this, actually, the computation graph for the node A, the next question is how to compute the embedding for node A. We do this from right to the left. What does this mean? This means we learn the embedding for A and C first. A and C, they are the neighbors of B. We learn the embedding for A and C first, and then we just do some aggregation and aggregated the embedding of A and C to get the embedding for node B. And similarly, we can get embedding for C and D. And then by aggregating the embedding of B, C, D, finally, we can get the embedding of the A. You see the such process actually nicely use the graph structure surrounding the A. And after we get the embedding of A, then we can just use the embedding to do any type of the classification or prediction. For example, let's say that we can predict this member A has a scale based on this embedding. Next, please. So the challenge of this graph neural network method is you have to travel a very large graph, and you don't know how many neighbors you are going to use. You don't know how many hops you are going to travel. Here we use the example 2 hops. If you go to, let's say, 10 hop or 6 hops, you almost travel the entire graph, which is billions of nodes and billions of edges, right? So that's the first challenge. How do we sample the neighbors? And the second challenge is how do we aggregate the neighbors to compute the embedding of the current node, right? So these are the challenges. I think we already discussed, right? So how to sample the k-hop neighbors. It's very time consuming because it requires k-step joins, and the training data can be extremely, the graph can be extremely big. So that's the challenge. Our solution is the next, please. Our solution is we use in-memory graph engine to create this data on the fly, to avoid actually the k-joins of in Hadoop, which is very time consuming. So, okay, next, please. Yeah, and we use the Deep Graph, which is a graph engine developed by Microsoft, and this graph engine actually outperformed other graph engines. It's also compatible with the Azure ecosystem, and we onboarded this Deep Graph to LinkedIn cluster, so we can actually do this graph traveling in memory on the fly. Right. Next, please. In the following, right, so there are some examples how we can apply the graph neural network to to build a relationship between 2 types of entities, right? So to construct a knowledge graph. And here we introduced one novel concept called taxonomy aware GNN. What does this mean? This means given a member, so we have members, neighbors, friend in social network. We call this social graph. And we also have members title, members skill, and we call this member attribute graph. In the meanwhile, we also have the taxonomy graph, which is the hierarchical structure between skills, the connection between title and the skills, those taxonomies graph. As you see, right, so we can combine the social graph, member attribute graph, and the taxonomy graph into a single joint graph, which is the right. It's a single graph. Okay, next. Yeah, and with this actually single giant big graph, then we can conduct some very complicated machine learning task. For example, let's say we can predict. Let's say if this member just put the technician associate in her profile, it's difficult to understand what kind of job this person is working on, right? Technician is very ambiguous, can mean anything. Associate, okay, we don't even understand what's the domain of the associate mean. So, which means that we need to predict, this person is a food service worker, and this person is an electrical technician. It's not a general technician. Then how can we make this kind of prediction? And this can be actually perfectly done by this giant graph, which actually combined the member social graph, combined the attribute graph, and the taxonomy graph. So it's perfect for this kind of very challenging task to precisely understand what kind of title, what kind of occupation this person is doing. Yeah, next, please. So yeah, here is another application. So again with this giant graph, right? So we can understand the parent-child relationship between two skills, right? So we built this parent-child relationship between the two skills, not only based on the taxonomy graph. We also leveraged the social graph. We also leveraged the member attribute graph. So we put all the graph connect them in a single graph and to predict this difficult task. Yeah, so that's the idea. Okay, next, please. And we did a lot of experiment and compare with the other baselines, and yeah, and we have some interesting findings. For example, one of the important findings is when member has very limited number of attributes, but the taxonomy graph actually really helps a lot. So yeah, next. Okay, this slide just simply tell you we are handling a very large graph, right? And in our GNN experiment, right, we have more than 2 billion nodes. We have 112 billion edges, and you can see our model actually scale very well to this large graph. Okay, next, please. And okay, this tell us actually how many GPU we used, and how many GPU we used, and how many time we need to train a GNN model. Yeah. Okay, a recap of all the technical stuffs. So we discussed the 3 technical tasks. The conclusions, we can use the multilingual word embedding to solve the transfer learning problem to cover multiple languages. And we also discussed how can we use the product to collect user feedback, and how do we design multiple products to mitigate the user gaming and the manipulation. How do we use the multitask machine learning framework to aggregate the feedback from multiple products to further mitigate the gaming. And we discussed actually the how to use the state-of-art graph neural network to construct the edges between member and the skill, or between two skills. So yeah, so this is the recap of the 3 technical stuff. Okay, so that's it. And if you have any question or feedback, yeah, you can reach out to me. My email is qhe@linkedin.com, or you can also connect to me in LinkedIn. I'm happy to answer any questions offline through the LinkedIn email. And okay, in the end, I went through today's slide a bit faster than usual because I want to save some time back. And I apologize for the inconvenience in the beginning. Thank you.
Awesome. Are you comfortable with staying on for a few minutes for questions in the chat as well?
Yes, thank you.
All right, thank you so much. So to start off, our first question is, how do you find the linkage in the knowledge graph? Is it just based on friend requests in LinkedIn? If there are other linkages, how do you make sure they're accurate and not manipulated?
Yeah, that's a great question, right? So as I said, right, so our graph has different type of the connections, and so that's why we for example, if we have social graph, the social graph means the member connect to member, right? That's a social graph similar to Facebook. And we have member attribute graph. This member has this title, this member has this company, this member is working in this company. And we also have taxonomy graph, means the relationship between two skills, and the relationship between the title and the skill, right? So we have different type of graph, and we connect them together to form a giant knowledge graph. I think your question is probably made on the social graph part, right? Just based on the friend request, which means the people connect to another people. That's the social graph part. So for social graph, it mainly depend based on the friend request. That's number one. But we definitely have more connections more than that. For example, let's say the member can follow another member without permission of the followee, right? So so this kind of follow graph, right? You don't need the permission, right? You don't have to send a request. You just follow the person. Yeah, we also use the follow graph in our giant graph.
And I guess just to clarify, so
Yeah.
For example, the social connection or social network graph, you guys are using homogeneous graphs, not also along with heterogeneous graphs as well? Or are they all just knowledge graphs where they have different entities or different entity relationships?
It's heterogeneous because of the so first we have the member, job, skill. Those are the entities, right? But then between the two entities, how many type of the relationship we have, right? So let's just use the member and the skill as one example, right? So the member can claim, I have this skill in my profile. That's claimed by the member, right? That's one type of relationship, right? And we also have the relationship actually called the endorsement. I put some examples there, right? So other people endorse you are expert in this skill, right? So we call this skill proficiency. So the skill proficiency is another type of the skill relationship, right? And sometimes actually the member also say, I want to learn this skill. That in LinkedIn, we have the LinkedIn Learning product to help the member to learn some course, right? This member doesn't have this skill, but she just want to learn. This kind of I want to learn relationship is another type of relationship exists in our graph. So that's why our graph is heterogeneous. And we maintain all this kind of different type of relationship between member and the skill. And the same thing can apply to other type of relationship. Like between two member can be friendship, can be one member follow another member, right?
That's fair. And I guess our next question is more about the infrastructure. Do you use Gremlin or Neo4j or Bolt language?
Okay. I think here is probably about the graph engine, because of the Neo4j is one type of the open source graph database, and LinkedIn has our own graph database called Liquid, and the Liquid actually is built on top of the Neo4j, but it's a LinkedIn version of the graph database, and we also serve our knowledge graph data through this Liquid graph database.
And is there a paper on the taxonomy aware graph, or
Yes.
is that something that's in-house?
Yeah, we have. So I actually put a KDD paper in the beginning introduction. We published in this year's KDD. So I think I already shared the slides with Jenny, right? So and
Yep.
yeah, so
so I guess the slides are you okay with sharing the slides later on after the presentation?
I think should be fine. Can I do a quick sanity check? And
Okay.
okay,
Yeah,
can
absolutely.
yeah.
We'll definitely follow up with you about that.
Yeah.
And our next question is, how do we deal with inherent bias in your data? Do you have any method to mitigate or being aware of this bias in the graph neural network?
Yeah, excellent question. So linking, right? We actually we pay attention to the equity a lot, fairness a lot. So there are multiple type of there are at least two type of bias actually that we pay attention. Number one is our taxonomy itself has no bias. For example, let's say I can use title as one example, right? So in Europe, there are a lot of gender titles, which means this title is only used for male and this title only used for female. So we make sure for each male title, we have a corresponding female title. If we don't provide this option, then our user has no option to pick up the female title, right? So that's one bias we try to remove. Make sure at the taxonomy level, we have the both female, male actually represented in the taxonomies. And then we need to, the second bias is our machine learning prediction bias in the when we build the ages between two entities. For example, in the past, we found actually we can predict the male has this skill with a higher precision, but we can predict the female with the skill with lower precision. The reason is usually the female profile is less complete, so that's why the machine learning model is less accurate. We need to remove this bias. How do we do it? And we collect more training data for female to make sure the accuracy for female is higher. So this is one bias is taxonomy bias. Another bias is the machine learning bias. We remove all of them. So yeah, and the same thing we should apply to the age, ethnicity, right? Not just the gender.
And I guess do certain languages translate better than other vector match for cross-lingual transfer learning for multilingual word embedding?
Excellent.
So,
excellent question. So answer is yes. The reason is we have English model, we have English training data. English is one type of the Latin system, right? And when you actually do the transfer learning for German and French, Italian, it's easier to get a higher performance because of there are a lot of commonality between the English and the German. So that's why actually it's easier to get the same word embedding for both languages. But if you apply the English model to the CJK, which is the Chinese, Japanese, and the Korean, the performance actually is very poor because these two languages, they are fundamentally different.
I see. And I guess just to follow up, what are some ways you've kind of tackled that with languages that are a little bit more fundamentally different, for example, in Chinese?
Yeah. So for CJK, which means if we have a lot of training data for Chinese, if we can train a good model for Chinese, then it's easier to transfer the knowledge from Chinese to Japanese. So that's why we need some benchmark for certain language.
I see. So it's not always the easiest, but you try and find the best representation and transfer.
That's right.
And our next question is a bit about the GNN. How deep is the GNN in your applications? Like how many layers? Because as each layer goes into more hops, right?
Yeah. So when you ask how many layers, so you can mean how many layers of the graph traveling, right? So in terms of graph traveling, we limited our number of hops as 2, which means because we believe actually after your second degree, let's say your third degree, fourth degree friends, you probably don't know this person at all, right? So the second degree is sufficient. So that's the number of layers in the graph traveling. But you also probably asked me the question, in the deep learning architecture, how many layers I have in the training. So if that's your question, then the answer is that's depend on the application. So for example, let's say for some application like when we combine the GNN with BERT, the NLP model, sometimes we use 6 layers of the transformer, right? But for some applications, probably 2 layers is sufficient. That's depending on the different application. But the like normal BERT is 12 layers, but we can reduce to 6 layers. So yeah, that's another kind of the deep. I don't know which one answer your question, but I just described 2 to you.
Okay. So yeah, it makes a lot of sense, especially with 2 hops, where if with a social network, we know that like I think it was like 6 degrees of separation. So if we had the 6 hop, like we know everyone.
That's right.
So I guess to ask a little bit more about when you're dealing with heterogeneous graphs, one of the difficulty is that to kind of when you're aggregating the data from edge entity relationships, is that a problem that you guys had where when you guys are training a model you guys could have thousands of different entity relationships and you would have to train each one of them for that model?
Let me try to understand your question. You mean, let's say between 2 nodes, if there are, let's say, 1,000 different type of relationship, do we have to train 1,000 different type of models?
I guess for the model itself, during the aggregation step, right? There you would usually, one way is to actually just create I think the edge features for each of them, right? And aggregate all that. Is that something that you guys had to do for the LinkedIn GNN, or was there a different technique in that regards?
I'm not sure I understood your question precisely. So if you don't mind, can you repeat your question one more time?
Yeah, absolutely. So from my understanding of, I guess, training on a heterogeneous graph, when you transfer a model like a simple GCN, a GCN would just do aggregation on one type of edge feature, or but then when you have multiple of those edges, one way of training is just accounting for each of the edge and doing aggregation for each. But if you expand that to 1,000, that would really be computationally intensive. Is that something that you guys have to overcome that, or just brute force?
Got it. Okay, got it. So okay, you try to understand actually in GNN particularly actually how to handle the multiple type of relationship between 2 ends. How can we do aggregation, right? So the answer is it's a weighted sum, and for each type of relationship we need a weight. And but how to determine the weight? There are multiple research ongoing. So the one popular baseline is just uniform weight, right? Let's say you have 10 types, each type of relationship just actually the 0.1 weight. So in our KDD paper, we do the supervised learning, which means we treat the weight itself as a parameter and to learn. And how do we learn? What's the objective function? So when you train this GNN, right, you can train it in an unsupervised way. You don't have any task in your mind. You just want to train the embedding for each node. For example, let's say you can use BERT. You can use the BERT as the framework to train this GNN. Then it's totally unsupervised, right? You just try to predict what's your neighborhood, what's your next word, like which is a BERT. But we can also apply this in a supervised way, which means for example, let's say we know we are going to use this GNN model to predict the probability you apply for this job, right? Then we have a task in mind, and that we collected some label data for this task. Let's say you actually applied for this job, which is a positive example, and you didn't apply for this job when we recommend this to you, is negative example. So we have this label data for this particular task, and we use this as a supervisor task to learn the weight of this sampling inside this GNN traveling. The sampling, including actually how to sample each neighbor and how to sample each type of neighbor. And this kind of weight can be learned, can be optimized for this particular task, which is exactly the paper we published in KDD this year.
Oh, yeah, that was exactly what I was looking for in terms of my question. I'll very excited to check out that paper.
And for quick extension, we are writing another paper to extend to this paper is when you do this sampling, right? You also need to consider the privacy, right? And how can you reserve the member privacy? How can you make sure or respect the fairness, for example? Are you sampling the male, female, sample different ID group, different age in a fair way? So that's our another ongoing work, right, in the GNN. Yeah.
Definitely, and looking forward to seeing that paper in the future as well. I think that's it for all the questions. Thank you so much, Qi, for joining us today.
Yeah, it's my pleasure. Yeah, thank you very much.
Awesome, and thank you everyone in the chat that's still here for joining us. Have a great day.